Okay, so I just wanted to go through nuclear fission and fusion, as that's been a fairly difficult topic you've been working on, most of you have been working on over the last week or so. Um, so hopefully this all works. So both nuclear fission and fusion are related to radioactivity, but they're not the same as radioactivity. They are things that we can do to nuclei to produce energy or to release energy from those nuclei. So fission is the method we use at the moment in every single nuclear power station in the world. There are no working nuclear fusion power stations, they're all fission ones. And fission is the splitting of a larger nucleus by firing a neutron at it to make two smaller nuclei and release energy. And this is the general kind of process that any fission reaction will go through. This is all about uranium-235. So that's uranium with 235 protons and neutrons added together. We start off with uranium. And remember, uranium is radioactive, but that's not the crucial thing with nuclear fission. We use uranium because it's the largest naturally occurring element on Earth. And the larger the element we use, the more energy we can get from it, the easier it is for us to do fission. So we fire a neutron, which is fairly slow moving, at the uranium, and there's a very specific range of speeds the neutron needs to be moving at to cause fission to happen. If it's moving too quickly, it will just bounce off the nucleus. If it's moving too slowly, it won't be traveling with enough momentum to actually embed itself in that uranium nucleus and cause it to split into two, which is what we want to happen. So neutron embeds itself in the uranium, splits into two fragments, and those two fragments are our waste products. We don't want those. Those are radioactive nuclear waste. In that process, 3 neutrons are also ejected. So the neutron plus the uranium is broken down into 2 nuclear fragments plus 1, 2, 3 neutrons. And those neutrons are ejected at really high speed. They've got lots of kinetic energy, and that is where the energy is being released. So the energy from a nuclear fission reaction is released as the kinetic energy of the neutrons. And then if we can slow those neutrons down, so they're traveling at the right speed again, and they happen to hit the uranium nucleus, they will make that uranium nucleus split into 2, and the whole process will continue. And for that reason, this set of stages is called a chain reaction. Once you start it off, it just keeps on going all by itself. And this then is a nuclear fission reactor. I don't know if I can move me over there. There we go. So this is our general kind of model of a fission reactor. You've got a really strong, thick wall going around the outside, and then another kind of strong container, because this whole thing is going to contain lots of very hot, very high pressure water, and within that will be radioactive waste. It's got to be all very tightly contained. You take your uranium, which we mine. It's just a metal we mine. Places like Australia, Canada have quite a lot of uranium. We put them into these rods. So the red strips there, the red rods are where the uranium fuel is going. We fire a neutron or a stream of neutrons at those uranium fuel rods, and fission starts to happen. Those neutrons are fired at the right speed. They slam into the uranium fuel rods, and the uranium starts to split, releasing new neutrons, 3 new neutrons. Those neutrons then have to pass through the moderator, which is this kind of blue box surrounding each of the fuel rods. Now, the kind of moderator we are interested in is water. So those blue containers, the blue rectangles, are water. As the neutrons pass through the water, they lose some of their kinetic energy. They're slowed down by the water. And that serves 2 purposes. If the neutrons are slowed down, it means they're more likely to cause other uranium nuclei to split, to undergo fission. Remember, the neutrons have to be going at just the right speed. So it enables the neutrons to continue fission to happen. And also, As the neutrons pass through the water and give up their kinetic energy to them, the water gets hotter, and hot water rises and it starts to come through this pipe here, go around here into this sort of column here. That column is called a heat exchanger, and the water cools down as it falls through that heat exchanger and goes back into the bottom of the reactor as cold water again. As it passes through that heat exchanger, its heat, its thermal energy, is transferred into a second stream of water coming through here and heats up that stream of water until, as that leaves at the very top, it leaves as steam. And that steam is used to drive around turbines to produce electricity. Because that steam in that tube coming through here hasn't been in contact with anything radioactive, it's free to be released, and it doesn't have any kind of dangers, doesn't present any dangers to people in the area around the power station. The water which is in the reactor, the moderator water itself, will be contaminated, and that will have to be treated separately and stored up and all the rest of it. And that's the big disadvantage of these power stations. There's lots of radioactive waste produced which needs to be stored up for potentially thousands of years. On the plus side, there's no carbon dioxide released, there's no greenhouse gases, we're not burning fossil fuels. It's not renewable, but it's not as polluting as many of the other non-renewable sources. You do need to keep the reaction under control, because if too much fission happens, if for every uranium nucleus 3 more are produced, if every one of the neutrons produced goes on to cause another uranium to be split, the reaction will soon get out of control and the whole thing will just explode. So you've got control rods here, these black lines going down. They can be raised and lowered depending on how fast the reaction is happening. So if the reaction is going too quickly, the control rods are lowered into the reactor and the neutrons are absorbed by the control rods. The control rods are made of a substance called boron, and that will soak up the neutrons. If the reaction needs to speed up, the control rods will raise up and more neutrons will be allowed to move around and to circulate and to keep the chain reaction going. So the future perhaps in nuclear power is this: nuclear fusion. Fission is the splitting of a large nucleus into two smaller ones. Fusion is the opposite. You take 2 small nuclei, you stick them together, they make one bigger nucleus, and they release energy. And this is, at the moment, we can't really do it properly at the power station. It takes more energy to kind of get the whole process going than what we get out at the end. So here we are doing fusion with hydrogen. So deuterium and tritium are 2 isotopes of hydrogen. Remember, isotope, same number of protons, different number of neutrons. Deuterium is hydrogen with 1 neutron. Tritium is hydrogen with 2 neutrons. You get them moving really, really fast, and this involves heating them up to millions of degrees. So you slam them together, and they've got to be going fast because we want them to get so close together to overcome the electrostatic forces between them. They're 2 positively charged objects, they're going to be repelling, and it takes a lot of energy to overcome that repelling force. Get them going fast enough, get them to stick, you get helium, and an extra neutron is kicked out, and it's the kinetic energy of that neutron which we are trying to harness in our power station. At the moment though, this works in stars, it works in atom bombs and hydrogen bombs, but we've not got it working in power stations yet. But remember, fission, the splitting of a large nucleus into 2 smaller ones; fusion, the joining together of 2 smaller nuclei into one larger one.